All right. Now, once again, the homework for chapter 5, just 5 questions, is due on next Sunday or this coming Sunday at 11:59. It's already posted out on in this week's module. You'll see it. I should have a quiz also done pretty soon for chapter 5. Chapter 5, I think, is of its own quiz. Chapter 6 and chapter 7 will probably have also its own quiz. All right, so today we're going to do chapter 6. So let me share the screen with you guys. And give me a second here so I can get chapter 6 open up. All right. We're going to again look at the ebook. So chapter 6, we're going to be talking about, at least beginning to talk about, what are called probability distributions. And specifically what's called a discrete probability distribution. What you need to know, number one, is what a random variable is. That's the first thing that we're going to talk about, is a random variable. And a random variable is a variable that can take on different values according to the outcome of a probability experiment. Okay. So you flip a coin once, and you have 2 possible outcomes, heads or tails. So those are 2 outcomes of the random of the probability experiment, and those would be the 2 outcomes for a random variable. Okay. Typically, random variables take on numeric values, and there are 2 types of random variables in general. One type of random variable is called a discrete random variable, where there's a limited number of possible values for it. One other aspect of a random variable before we get to look at what a discrete random variable looks like is that it is not just a list of values for the variable, but it's also a list of the corresponding probabilities for each of those values. Okay, so a random variable has, of course, it's just particular values, but a probability distribution would be the values associated with that variable along with their corresponding probabilities. All right, so you'll get to see what I mean in a minute. So a discrete random variable, they say, for example, in a given group of 5 children, the number who got at least 1 electronic toy for Christmas would be 0 up to 5, right? Out of the 5 children, assuming they only got 1 toy a piece as a possibility. So electronic toy a piece. So either none of the 5 children got a toy, or 1 of the 5 got an electronic toy, or 2 of them did, 3, 4, or 5. All right. So again, we're assuming only 1 toy per child. And so those are the possible values for this random variable. And what is the random variable? The number of the children who got at least 1 electronic toy for Christmas. Okay. So random variable runs from 0 to 5 because there's 5 children. You're very clear about that? Okay. So a random variable has to be defined. You have to define what it is. Typically, we use the variable x to define a random variable. And then we just list their values. All right. A continuous random variable can take on any value along an interval. Any value along an interval. All right. So you can picture things like temperature, things that we measure typically are continuous random variables. Now, the measuring instrument itself could have a limitation on the particular values that you can have. right? It could be a limited number of values because of the measuring instrument. But theoretically, if you had a very, very precise measuring instrument, you could picture having an unlimited number of values in between 2 points on a number line. And that would be a continuous random variable. Now, with continuous random variables, we don't talk about probabilities at any particular point because we have an infinite number of points in between in an interval, and therefore the probability at any one of those points is considered to be 0. All right? There's no probability associated with any point along a number line if we're dealing with a continuous random variable. Okay? With discrete random variables, each value that the random variable can take upon itself, each value has an associated probability. So we can talk about the probability that x is equal to some value with a discrete random variable. We can't say that with continuous random variables. We have to say something like the probability that you got less than 5 or greater than 5, something like that, or between 1 and 5. It has to be an interval. We have to talk about intervals with continuous random variables. All right. Any questions about that? You probably maybe have some idea about this from before, but I just wanted to go over it with you. And the book does a decent job in describing what these things are. All right. A random variable is described as random because we don't know ahead of time exactly what value we'll have when we actually run the experiment. Okay. In algebra, we talk about variables, but we know we know under certain circumstances exactly what value we're going to get. Okay. So it's absolutely for sure this is the value we're going to get. But with a random variable, we don't know. Unknown. For example, if we toss a coin, we don't know whether we're going to get heads or tails. If we roll a die, we don't know whether we're going to get a 1, 2, 3, 4, 5, or 6. Okay. If we measure the like it says here, measure the diameter of a bearing, we don't know in advance what the exact measurement will be because there's variability whenever something is produced, right? There's some variability because of the way the machines are created. They're not that precise. So there's always some degree of variability in real life, and that's where the word random comes in. All right, now that we know what a random variable is, we can talk about a probability distribution based off of that random variable. So a discrete probability distribution is a listing of all possible outcomes of the probability experiment. That is all possible outcomes of a random variable, along with their respective probabilities. Okay, so it's actually 2 lists, right? The values and the probabilities. Let's look at an example. Experiments conducted in which a fair coin is flipped twice. The result of the experiment will be a random variable, which is equal to the number of times that heads comes up. Okay, so it's flipped twice. Tell me what are the possible values of the random variable? Random variable is the number of times that you get heads when you flip a coin twice. So what are the possible values for the random variable?
0, 1, or 2.
That's right. You either get no heads, or 1 head, or 2 heads. Now here's the trickier question. What are the probabilities associated with those 3 occurrences? For example, what's the probability of getting 0 heads?
1 in 4.
That's right, 1 in 4. One way of figuring it out is that there's 1/2 probability for flipping at once, and because the events are independent of one another, flipping a coin, right? Each flip of the coin is independent of any other flip of the coin, then you simply use the multiplication rule, right? 2 heads, 2 tails, which would be no heads, right? Would be 1/2 times 1/2, which is 1/4. How about, what's the probability of getting 1 head?
1 1 and 2.
That's correct, because there's two possibilities. Either the first flip is a head, the second one is a tail, or the first flip is a tail and the second flip is a head, right? In both cases, it's 1/4 when you multiply 1/2 times 1/2. And it's, therefore, it's 1/4 plus 1/4, which is equal to 2/4, which is a half. And then what's the probability of both flips leading to heads?
1 and 4 again.
1 and 4. All right. Here they are, right? They listed all four of them. Heads, head, the first letter here represents the first flip of the coin. Second letter, the second flip here, or all four of the options, right? Now notice that options 2 and 3 here, HT and TH, represent one head, both of them. And they're mutually exclusive events, aren't they? Mutually exclusive. Therefore, you can add them, right? Once you calculate them, which is 1/4 apiece, you add them and you get 1/2. Here's a rule about probability distributions, right? Actually, there's two rules. What constitutes a probability distribution? Because you list values and you list the probabilities underneath them doesn't mean you have a probability distribution. Probability distribution means that the probabilities themselves, and of course this is by definition, all those numbers are between 0 and 1, right? All of them that are listed. And secondly, that they all add up to 1. That's because they encompass the entire sample space. And the probability of a sample space is equal to 1. So probabilities must always add up to 1. If you see a list of values and probabilities, and the probabilities do not add up to 1, that means that's not a probability distribution. On the other hand, if they add up to 1, but the individual so-called probabilities are not between 0 and 1, that is, you might find a negative number as a probability. You might find a number that is bigger than 1. But you might, let's say, oh, but they all add up to 1. Well, that doesn't mean it's a probability distribution. The individual probabilities have to be between 0 and 1. So there are two requirements. Each of the probabilities are between 0 and 1, and they add up to 1. Both of them have to be true. Both those two things have to be true, and then you have a probability distribution. So you can picture on a test. I can give you something, I'll show you what they look like, the typical way of displaying a discrete probability distribution. But I can give you one and say, all right, here is a table. Is that a probability distribution, right? And if it isn't, tell me why it isn't. Something like that. You can picture I can create a multiple choice question based on that. And I do that, and when I teach the 111 course, Math 111, which is the Intro to Stat course, I typically have a question like that on a test, and sometimes it shows up on their final exam also. Okay. So here is one way of displaying a probability distribution, where it's displayed vertically. You can display this horizontally or vertically, where you have your listing for X, and then P of X is the probability of that event, all right? Or that value of the random variable. This is you can only display this for discrete probability distributions. You cannot display something like this for a continuous probability distribution, all right? Again, individual values are meaningless in the continuous world, all right? Only range of values are meaningful. But in this chapter, we're dealing strictly with the discrete case. All right. And of course, we could do something like this, right? You could do this here. The number of heads, 0, 1, and 2. Is this sort of a histogram? Well, sort of like a histogram, right? It sort of looks like a histogram, but it also sort of looks like a bar chart, right? But it doesn't really matter because the y-axis here, the height of these rectangles are what? They're the probability, or another way of saying it, relative frequency for those particular values. So a probability is not just if we select somebody at random, right? And we say, what's the probability of whatever the question is. But it also gives us the relative frequency, the percentage of the population that would end up with that result. All right, you get the idea? So we can ask questions with probabilities based off of randomly selected one individual or one case, or we could say, what is the percentage of cases? All right, we could say over the long term. That's also the same probability. Probability can be expressed in two different ways. Any questions about that? Make sense? Okay. And then here's some characteristics of a probability distribution, which I mentioned before. For any value of x, the probability obviously has to be between 0 and 1. And the values of x are, and they're using kind of a fancy term here, right? Exhaustive. That means you've included all possible values of that random variable. Right. And that they are mutually exclusive from one another. That's why you can add them. All right. Right? There's no common values. There's no common elements between each of those values. It can only occur once in a given experiment. And of course, the sum of them, all these probabilities equal to 1. So they're being very mathematical here, right? Typically in the books, they only mention number 1 and number 4, but they're trying to be fancy here by saying we're including all values of x and that each of them are mutually exclusive from one another, which means we can simply add their probabilities, and then they all add up to 1. So, nice little definition, I think. All right. Discrete probability distributions are often based on classical probabilities, but they don't have to be. There are some famous ones that we'll talk about, in particular the binomial. All right. If we don't get to it today, we'll definitely get to it on Thursday. And then we'll also talk about a couple of other ones, which tend to show up here and there. We'll mention those next time. Now, here's another case. Here's another example. Now, one of the things you have to do when you read a word problem is determine whether it is, if they do ask for a probability, determine whether you do have a probability distribution. That's number one. And number two, you have to define what the random variable is in the particular problem. All right, it has to be defined. Now, here's an example. Financial counselor conducts investment seminars with each seminar limited to 6 attendees. Because of the small size of the seminar group and the personal attention each person receives, some of the attendees become clients following the seminar. For the past 20 seminars she has conducted, X, which is the number of attendees who become clients, has had the relative frequency distribution shown in figure 6.2. So hopefully they show you 6.2. Oh, here it is. Now, obviously, this is, again, some sort of histogram. It looks like a histogram, but it's actually just a display of a probability distribution. It's not really clear from this graph what the exact values of these are, right? I mean, you can guess at them. It looks like the ones that are in line with the notches along the y-axis here are exactly those numbers, and then the ones that are in between looks like they're halfway in between these here. So, for example, the number of attendees who become clients, it looks like this bar is halfway between 0 and 0.1, so we'll say 0.05, all right? A table would be better, right? Because we're guessing it's 0.05, it could be 0.45, it could be 0.55, it's possibly something else. This one is 0.10, this one's 0.2, this one's 0.25, this is again 0.15, 0.15, and 0.1. If we added them up, let's say we add them up, we end up with 0.15, 0.35, and 0.25 is 0.6. And this is said 0.6, 0.75, 0.9, and then 1. So it looks like they add up that way. And then they actually are displayed this way also. This is the best way of displaying it, correct? Because then you know exactly what the probabilities are. What? I guess correctly. All right, so this is your probability distribution. They all add up to 1, and each of the individual probabilities are between 0 and 1. These are, because you can have because you typically have 6 people at a seminar. What X is the number of those attendees who convert to clients, right? Who become clients. Well, it's possible that none of them at the seminar become clients. It's possible one of them will become clients, 2 out of the 6, all the way up to 6 out of 6. By looking at this probability distribution, tell me what the most frequent result is. The most frequent result would be what?
3.
3, okay, because 1/4 of the times that happens, right? But what if I ask the following question? What is the average number of attendees who become clients? What is the average number? Well, what the answer you just gave me is not the average. I just asked you what the most frequent one is. That is 3 attendees. But what if I said over the long term? What is the average number of clients? Now, when you answer that question, you cannot round to the nearest whole number. All right? In these types of questions, when you're dealing with an average or mean of a probability distribution, we must give exactly the answer with the decimal, even though it doesn't make any sense if we're talking about people or things, right? I mean, if the answer was 3.1, well, does that mean it's 3 people plus 1/10 of a person? You know, maybe their eyeballs or something. I don't know, right? No, it just means over the long term, that's the average. Okay. We say the same thing for if we want to know the standard deviation of a probability distribution. Okay. It's the average spread between these values. All right. Now, how do we calculate the mean, and how do we calculate the standard deviation? All right. So now in Excel, it's pretty easy to do this. If we did this in Excel. So actually, I'm going to open up Excel. I think I did an example like this in Excel before. Let me just stop sharing for a second. Here we go. This one here. Just give me a second. Just need to open this one up. I created it the other day. There we go. All right. Let's go back to you. All right, so this is a random variable that has 10 values. All right, 10 values here. And suppose these are the probabilities. So this is, just type in X here. This is X. And this is P of X. All right. And let me just center this a little bit. All right. Suppose, so this row here is the random variable values, whatever it might be. All right, I'll tell you what it is actually when we get to it, but I'm not telling you right now. And this is just the individual probabilities. Notice that I just did a little sum here, added up all the probabilities equal to 1. Okay. Now, if I wanted to find the mean of this, so the way to write the mean in the language of statistics, you could type out the word mean if you wanted to, but typically they write it this way. E parentheses X, all right? And E parentheses X is called the expected value of the random variable. So E of X is the mean, same thing, expected value. Expected value means what is the expected value of the random variable over the long term? Okay. So now we have our values here from 0 to 10. How do we calculate the mean, the expected value? Well, one thing we can do, and let's just get rid of this right now. I'll talk about that. Let's say right below here, on this row here, we're going to multiply the value times its probability. We're going to say X, and then we'll have times, and then we have P of X. All right. So that's going to be what I'm going to display below that. X times P of X. Now you're asking, why would I do that? Okay. And that's a legitimate question. The reason why I want to do that is because when we calculate, if you remember the case where we had a histogram, remember the histogram case where I asked you to come up with an estimated mean of the histogram? Remember that? And what did we do? We found the midpoint for each of the classes. And then what did we do? We multiplied the frequency times the midpoint. Remember that?
Mm-hmm.
And if you remember, the formula was the sum of the midpoints times the frequency divided by the sum of all the frequencies, right? Well, a frequency divided by a particular frequency divided by the sum of all the frequency is the relative frequency. Or, in this case, probability. It's the same thing. So X, in this case, is not a midpoint. It's the actual value of the random variable. So X times the relative frequency, if we added them all up, what are we going to end up with? The mean. It's the same formula that we use for the mean of a histogram. Okay. So that's what we're going to do here. We're going to simply create a formula, and we're going to say this number, right? And then times this number. C3 times C4 in this case here. It's going to be 0, right? But that's not the important point. We're going to copy this formula in Excel, right? We're going to copy it across all the other values, right? We'll even copy it where we have the sum formula, okay? And do paste. Now forget about this here for a minute. Just get rid of that. Here's X times P of X right here. See it? For each of the individual values of the random variable. See how easy it is to do it in Excel. And then the E of X is just the sum of that. So we'll just say equal to sum. And then we'll just take the sum of all these numbers of these X times P of X. And that's our expected value. That's our mean, 4.5. This is sort of a weighted mean, isn't it? It's a weighted average because each of these values have their individual probabilities, and these probabilities, you can also consider them to be weights. So this is a weighted average, okay? So somebody might say, oh, what's the mean of the random variable X? What would they do? They would add up all these numbers from 0 to 10, right? And there's 11 of these numbers. So we'll say, all right, I'm going to add up these numbers. What happens when you add up from 1 to 10 here? You get what? What's the answer? Let me see if I remember. 110. I think you get 55. All right. There's a formula for doing this, which not necessary for this course, but 55 is the sum of these numbers here from 0 to 10. And they'll say, all right, 55 divided by 11 is 5. But that's not what you just did was not a weighted average, right? You just took the simple average of those random variables values. But notice the answer is 4.5 because a relative frequency, unless the probabilities here or relative frequencies are all equal to each other, the simple average is not going to be the same as the expected value of the probability distribution. It's going to be different. And in this case, it's 4.5. It's 4.5. And I can tell why it's 4.5, right? Because most of the probability is occurring, well, if you added up all these probabilities, let's say from 6 to 10, and then from 0 to 5, you'll find that most of the probabilities are where? At the lower value. Yeah. That's why it's a little bit below 5. That is our mean of a discrete probability distribution. It's pretty easy, right? If you just understand that it's the same formula we use for a frequency distribution. Now, how do we find the the standard deviation of a probability distribution? Well, the first thing we have to do is calculate the variance. The way to write variance in the probability world, it doesn't say in the book, but we would write it this way: VAR, and again, we say X in parentheses. That's the variance of the random variable. That's how we write it, VARX. Now, how do we calculate it? Well, what we're going to do is something very similar to what we do when we calculate a variance in any case, right? We take the individual value and subtract the mean and then square it, right? The deviation from the mean, square it. But in this case, what we have to do, and we did the same things, well, the formula was a little different, but we did the same thing with our frequency distribution. We multiplied the square deviation from the mean by what? By the probability, by P of X. So that's what we're going to do in each of the cases here. We're going to create a formula, and we're going to say, open up a set of parentheses, and we're going to just point to the value for that particular value. In this case, it's in C3. And then we're going to subtract what? The mean.
4.5.
Yeah, but because of the way Excel works, we want to fix the position of the mean for each of these other values here. So the way to do it is we want it to be in C8 in all these cases, right? We want C8, so we fix it by putting a $ before the 8. It fixes the 8 in all the, when we copy the formula over. It makes it C8 for all those cells. Otherwise, if we didn't do that, then the next one would say C9, right? The way Excel works, C10 as you went across. So we don't want that. We do want the first number to vary, right? According to which column you're in, but we don't want the second one to vary. And actually, I'm wrong about that. It should not be C. It should be the $ should be before the C, not before the 8. So I apologize. It's the column that needs to be fixed, not the row, right? So there you go. So you put your $ before the C because it's the column that's going to change, and we want the column to be we want the column to be C in every case. The row is going to continue to be 8 all right. Now what we're going to do here is square this. So we're going to close the parentheses and do a caret 2. That squares it. Now you don't have to worry about parentheses here because the order of operations is that exponents occur before multiplication, right? So you don't have to worry about this. You can simply say multiplication multiplied by, right? And we're going to multiply it by its probability. So what it's going to do here is it's going to take the parentheses and take it to the second power, square it, and then it's going to multiply the result by C4. And then we copy this formula all the way down. Okay. Now, what I should have done, to be honest with you, I'm going to actually cut this and move it down one. All right, so this is fine. I can actually put this in here, right? I can put in what I just did. I could put in x minus e of x, right? Quantity squared. Maybe put another parenthesis around this. And this is times p. Right? So just so we can display everything, I'll just click that. All right. So this is the product of the probability times the square of the deviation from the mean for each of these values of x. All right. And then the variance is simply the sum of all that. All right. And then the standard deviation of x. Now, typically we'll write that, we can write that with sigma if you wanted to, sigma x, right? And what I'm just going to do here is just type out standard. This is not the way you typically write it. All right, but you get the idea. Just the square root of this number up here. I think we could type in square root, right? Square root. Here. All right, and then if we want our answer to be maybe in 3 decimal places, right? We'll do a, we can round also, right? We can do a round here. So do round. Gets to 3 decimal places. Yeah. All right, so we got our answer. The mean is 4.5, and the standard deviation rounded to 3 decimal places is 1.573, and that's our answer. That's how you figure out the mean and standard deviation using Excel of a probability distribution. So I'll post this. Let me save it first. I'll probably rename it or something, just talk about it. So this particular one, we're going to use again a little bit. Now, this is, by the way, what is called a binomial distribution. We haven't talked about it yet. And there is actually, for the mean and standard deviation, there's an actual formula that we can use, as opposed to going through all of these calculations. But the formula will, for the binomial, will match these answers. Okay. But we'll get to that in a little bit. All right. Any questions about how to find the mean or standard deviation of a discrete probability distribution? Yeah, so you have to list the individual values, you have to list their probabilities, and then everything else you can do in Excel. This can be done in Minitab too, and the book shows you how to do it, but it's so easy to do it in Excel. My feeling is just show it to you in Excel. I mean, you'll both have Excel on your computer, and why bother doing something like this in Minitab when it's so easy to do it in Excel? All right. No questions? So you're good with this? Okay. Let's go back to the book. All right. So what this next section is basically what we just covered, right? Just covered this. How to determine the mean and variance, or in the standard deviation. Because typically when people ask about the probability distribution, they're asking about the mean and the standard deviation. Although sometimes they do ask about variance too, or they may mention variance, but typically the standard deviation is what you're interested in because it's in the same units as the mean is in. So here again, if you look down here, they put E of X as the expected value or the mean. All right. You could use sigma if you want for the standard deviation, but the way to write it would be sigma, and then as a subscript, put an X next to it. So you would write sigma X as a subscript. And that indicates that's the standard deviation of the random variable X. Because you might be talking about maybe a random variable X and another random variable Y, right? It's possible in the same discussion, you could have two random variables. You want to distinguish between the two. You could use, of course, mu also as the mean. Okay, you could do that too. All right, so they're getting a little fancy here with the notation. But notice that the variance is exactly what we did in the Excel spreadsheet. This is except I used E of X instead of mu, right? Expected value of X for the mean. But it's the same formula, right? It's the sum of each individual value of X from the mean from each individual value of the random variable squared times the probability for that particular value of the random variable, and you add up all of them and you get your variance. The mean, we just add up the product of each individual value times its corresponding probability. We add them all up and we get the mean. Now they have these alternative formulas here. I don't know why. Maybe in the past, before they had Microsoft Excel, right? People had PCs. Before all of that, these formulas probably were worthwhile because computationally they were a little easier to do than the original formula for the variance. I see no value of doing this, using this now. Maybe somebody could argue that even with a computer, it's computationally more efficient to use this formula as opposed to the original formula. But for our purposes, with using Excel, I don't see any value, right? Because you're just creating a formula in one cell and then copying it over to all the other, right? All the other values. So you could use it if you want. I just think this alternative formula loses its intuitive meaning, right? Because the original meaning is that it's the probability times the square deviation from the mean, right? And you add them up. That's your variance. You look at this and you say, what the heck's that mean, right? I mean, how do you say this in words, right? It makes sense for you to remember. I wouldn't be able necessarily to remember this. So I think it's worthwhile, since we know how to use Excel, to use the original formula because it's something you can remember, in words. And if you want to use this alternative, you can if you want. But again, I don't see any reason for it. All right. Anyway, they, for the problem they gave, they came up with the answers, right? For the original problem with the 6 clients, and how many of them converted over to, the 6 attendees at a seminar, and how many converted over to becoming clients. So for each of the values of the random variable, you multiply the probability times it, and you come up with 3.2 attendees. So please don't round this answer. All right, you don't say, all right, I'm going to round it to 3. No, that's not the answer. The answer is 3.2. All right, so whatever you get is the answer. If there's a decimal there, don't worry that it means a part of a person. It doesn't matter. All right, it's basically an answer over the long term mean. So please put the complete answer there, and that's it. And the variance, of course, they use, of course, the original formula here. You see it, the original formula. And the variance is 2.66, and then they took the square root of that to get the standard deviation, if that's what they're being asked for, right? So how do you interpret the 3.2? So that's the expected value or mean of X, and it will tend to be the average result if the probability distribution remains unchanged, and a great many such seminars are conducted in the future. So what if you're trying to determine how much to spend on one of these seminars, right? Don't you think it's worthwhile knowing how many, on average, how many clients you get out of the seminar, right? And then you can maybe multiply that by, you can come up with some calculations that tell you whether the benefit, right, is whether it's worth the cost, right? That's where it comes in, because you want to know over the long term, is this worthwhile for me to do? Or maybe I should just do something else instead of doing seminars. Maybe I should get people some other way. That's why you have to use the exact expected value, because it gives you over the long term the cost or the benefit, whatever you're calculating. All right, does that make sense to you? Yes, okay. Stop me if it doesn't. Now, a uniform distribution, discrete uniform distribution. All right, what the heck is a uniform distribution? Well, I'm not going to spend a whole lot of time on a discrete uniform distribution, although it does occur here and there. Let's see what it means. It's talking here about the Pennsylvania State Lottery, all right? That's some sort of daily number, a 3-digit number selected at 7 p.m. each weekday. Numbers obtained from the first ball that pops from each of 3 machines containing balls numbered from 0 to 9, all right? This event is televised, blah, blah, blah. Okay, whatever. All right, so you end up with you have 3 machines. You're going to have 10 possible balls that can come up, right, for each of the machines. All right. So that's basically what it is. So it's a 3-digit number here you're getting, and the number ranges from 000 up to 999, right? Now you can picture that each one of those balls, each of these numbers should be equally likely, right? It should be, right? What's the probability of getting the 0? Well, getting a 0 in the first position would be 1 out of 10, right? And then the second 0, 1 out of 10 again. The third 0, 1 out of 10, right? So what's the probability of getting 0, 0, 0? It's 1 out of 10 cubed, which is 1 out of 1,000, right? So, and the same thing with the 999. Each of the and there's 1,000 of these combinations, right? From 000 to 999, there's 1,000 possible numbers. So it makes sense. It's 1 out of 1,000. All right. We can express that as 0.001. So here, lottery officials rigorously weigh the balls and conduct extensive testing, blah, blah, blah. All right, so they want to make sure the probabilities are equally weighted. All right, so we have equal probabilities. We know that for sure. A number of years ago, an individual was convicted for injecting latex-like substance that made some of the balls heavier. All right. As a result of this one-day non-uniformity of the probability distribution, security was heightened considerably, and officials are now more scrupulous to make sure, I guess, that all the balls weigh exactly the same. All right. All right. Despite the uniformity of this discrete probability distribution, some players still insist on playing a lucky number based on their birth date, wedding date, or digits from an auto license number. Some even avoid playing yesterday's number because they think it's been used up for a while, right? But that's not true, right? It could come up again. Many seem to prefer 333 or 777, blah, blah, blah. All right. A discrete uniform distribution means what? All the outcomes are equally likely. That's what it means. All the outcomes are equally likely. So if we think about all the outcomes and we want to know the expected value, this is the one case where we can do the simple average of the values and come up with the expected amount, right? Because all the probabilities are the same. If we listed all 1,000 of these numbers, right? Picture listing them all the way across the page. We know each of them had a probability of what? 1 out of 1,000. We multiply the values times the probabilities. Every single one of those values is being multiplied by 1 over 1,000. So you can picture just doing what? Factoring out 1 over 1,000, just adding up all the numbers and dividing by 1,000. Isn't that the same thing as just taking an average? Isn't it? So this is the discrete uniform distribution, mean that the simple average of all the values is your expected value. We just calculate it the normal way. Same thing we would do. Now with the variance, we have to be careful. All right, we have to calculate it the way we should be calculating. But as far as the expected value, the mean, it's going to be the simple average. Variance, we have to calculate the normal, the way that I taught you on that spreadsheet. So am I going to test you on the uniform? No. But there are cases, like the one we just talked about, where the probabilities are equal. And here they give you different cases here where you're supposed to calculate the mean, variance, and standard deviation of each one of these. And again, you can do it by hand with a calculator, right? Or you can use a spreadsheet. And since you're going to be doing your homework, you're going to be doing quizzes, tests, you're doing it all at home. You have your computer there, right? I'm saying you can use your computer, use the tools that you have. Might as well use Microsoft Excel. It's easy, right? Saves you a little bit of work. As long as you feel comfortable in creating that little table there, you should be able to do it pretty easily. All right. Anyway, let's move on. I'll assign some problems like this. I think I've already assigned some of them. An example also comes up also where the random variable might deal with money, such as profits. In other words, they might give you for each, they might give you, let's say, revenue with a particular probability, and you have a bunch of revenue possibilities. You have expenses, right? And you're being asked to come up with a probability. They may ask about the expected profits, right? Expected profits. So you know that revenue minus expenses is profits, right? So there are problems just like that, like the one we're seeing right here. All right. Well, let's see what this says. Laura McCarthy, the owner of a bakery, has been approached by insurance underwriters to try to convince her to purchase flood insurance. According to local meteorologists, there's a 1% probability that the river will flood in the next year. Riverside's profits for the coming year depend on whether Laura buys the flood insurance and whether the river floods. Okay. The profits, which should take into consideration the $10,000 premium for the flood insurance for the 4 possible combinations of Laura's choice and river conditions. So let's take a look at this. So here's a little table they give you here. And what's the table here giving you? It's giving you the profits based on what? The conditions of 2 things. Whether you get flood insurance or not, and whether the river floods or does not. Okay. So look at the table. It says if you have no flood insurance and the river floods, you may lose $1 million. All right. You might, this is the person's bakery, and they may lose everything, and maybe it comes out to $1 million loss. Now, what if the river doesn't flood? Okay, what does the 200,000 mean here? It means, well, if it doesn't flood and you don't get insurance, you've made $200,000 in profits for that year. Okay, so on the one hand, you lose $1 million. Now that $1 million may include losses of revenue, right? Maybe just not only property but revenue. You lost revenue, but that's your loss. You lost $1 million if you don't have insurance and floods. If the river doesn't flood, you make $200,000 because it's just normal case. What if you buy the flood insurance? Well, the flood insurance costs $10,000. Okay, costs $10,000. Now assume here that if the river does flood, the insurance pays for everything. It recoups all your losses, whatever they may be. All right. So if the river doesn't flood, what ends up happening? Well, you end up if you don't have insurance, you get 200,000. If you do buy the insurance, you end up with a net 190,000 because you paid $10,000 of your profit for the insurance. So you end up with 190,000. Now, if the river floods and you get flood insurance, okay, the policy says in this case here, you get back what you should have earned if you didn't have insurance and the river didn't flood. All right, in other words, it makes you whole. So that's why the 200,000 is sitting here. Now you might say, well, what about the $10,000 insurance? Well, it says that it'll even pay for the premium. All right. Basically, it puts you in the same situation as if the river didn't flood and you didn't have insurance. So these are the scenarios here. And it says the probability of the river flooding in the next year is 0.01. And the question is, if the lawyer decides not to purchase flood insurance, right, use the appropriate discrete probability distribution to determine Riverside's expected profit, the bakery's expected profit for the next year. So they're saying she didn't buy the insurance. So what's the expected profit? How would you figure it out? Well, there's two cases. The river floods or it doesn't flood, correct? If the river doesn't flood, the expected profit's 200,000, but what's the probability of that happening?
0.99.
0.99. So the probability of it not flooding, and you don't have insurance, right? The amount that the expected profit's 200,000, right? If it does flood, you have a loss of $1 million. So it's negative. You could say profit of negative $1 million. What's the probability of that happening? 0.01.
0.01.
Right. So how do you find the expected profit if Laura didn't purchase the insurance? It would be 200,000 times 0.99 plus negative $1 million times 0.01. So it ends up being negative 10,000, right? Plus 0.99 of this, which is what, 198,000, right? So 198,000 minus 10,000, 188,000, right? I think, if I'm doing my arithmetic correctly. So she's saying, all right, he feels pretty good about that, right? Her expected, but she misunderstands expected value, because expected value says this is the long-term average amount based on the fact that there's a 1% probability of it flooding any particular year. Now, what does that mean? That means in every 100 years, you expect it flooding in one of the years, right? What's the problem with that? Well, it could be that it's this coming year that it floods. And if she loses $1 million, she's out of business. So if I'm the insurance salesperson, right? I'm going to emphasize that to her. She'll say, well, I took this statistics class, and my expected profit over the long term per year is $188,000. I feel pretty good not getting this flood insurance. Then I counter and I say, that might be true over the long term, but what if the river floods this year, right? What if it's this year that happens? You're going to lose $1 million and you're going to be out of business. And then then Laura gets, ooh, I'm a little bit shaken by that, right? So then she asks the following question: what's her expected profit if she purchases the flood insurance? So she says, all right, you got my attention. All right, what's my expected profit if I buy the flood insurance? Well, it's the same probabilities, right? It's 190,000 times what?
0.99.
0.99. And it's 200,000 times 0.01. Now, if you figure out that expected value, is it higher or lower than the expected value without flood insurance?
It's higher.
Higher. And then you say, all right, over the long term, you're going to make more money. And then you could say, but if it floods in the next year, you're protected. And then Laura says to him what, or her, whoever the insurance person, I love you. Yeah, absolutely. I'm going to purchase the flood insurance. So originally, Laura's like really cocky and she's thinking, I don't need it. But a good insurance person will say, well, what if? Gives you a what if, right? And then she said, all right, what's the expected amount with the insurance? And then you could say, all right, looks like I'm going to make even more. It's easy, right? It's an easy decision for Laura in this case here. All right, any questions about that? So that's a typical type practical question that could come up with this sort of thing. Just checking the time. All right, so let's just take a quick look at the next section. I think the next section is the binomial. And it just tells me my product session has expired. And well, how do you feel? Do you want to go another 10 minutes?
It's fine with me.
You feel okay with it, Han? You want to go another 10 minutes? Okay. So give me a second. I'm going to re-enter my password. Get right back in. All right. Hopefully Cengage is, okay, here we go. Get to chapter 6. Chapter 6. Binomial. All right. Okay. So we'll at least introduce you to the binomial. So the binomial is a special discrete probability distribution. So this is the most important of the three that I will show you. I will show you all three that the book talks about, so that you're, because sometimes I think in introductory courses, you just learn the binomial and that's it. You don't get a feeling that there's many more, but there's many discrete probability distributions, and these special ones have formulas. That's the whole point. They have special formulas for calculating the values of the random variable, and also sometimes the mean and the variance or standard deviation of the random variable have special formulas. So the binomial is an experiment where you have a certain number of repetitions of the experiment, we call them trials. All right, that's the term that we use in probability. So we have consecutive trials where there are two possible outcomes, not more than two, just two, in each trial. In each trial, all right, that's important. Now, in each trial, they call it a Bernoulli process, Bernoulli, which means basically you have one or the other as possible outcomes. Each one of those outcomes, the two outcomes, have a probability associated with them, with the sum of the probabilities being equal to 1. For example, the simplest one is just flipping a coin, right? And the Bernoulli says you have either a head or tail, and the probability of heads is 1/2, probability of tails is 1/2. Right. It's two outcomes. But you can make any probability distribution into a Bernoulli by simply picking one of the outcomes and then saying not that outcome. For example, if you roll a die, you know you have 6 outcomes, right? From 1 to 6. But you could say, have 2 outcomes. Say, outcome of rolling a 2, and then you could say the other outcome is not rolling a 2. Can you repeat what I just said? Because you were both looking away when I said it. So can't even see you. I don't even know what you're doing. I know you're paying attention, but I can't see your face. So there are 2 outcomes in a Bernoulli process, and you can make anything into a Bernoulli process, discrete, by just saying what's the probability of something happening or it not happening. So if you flip a coin, it's naturally two outcomes. But rolling a die, you can make into 2 outcomes by picking one of the numbers, like a 2, saying what's the probability of 2? It's 1 out of 6. What's the probability of not getting a 2? 5 out of 6. See what I'm saying? So you can always do that. Now, so there's 2 outcomes. You call one of them a success and one a failure. What's a success? It's just one of the outcomes. You just pick it and call it a success. The other one you call a failure. All right? I don't know why they come up with that terminology, but that's what they've come up with. But you can say yes, no, whatever. The other thing, the probability of a success, which implies the probability of failure, remains the same for each trial of the experiment. It doesn't change. Right? So each of the trials are independent, number 1. Number 2, each of the trials has 2 outcomes. And number 3, the probabilities of those outcomes remain the same from trial to trial. Make sense? That's called a binomial. Period. And what is the random variable? The number of successes in n trials. So typically they use the letter X to represent the random variable, which is the number of successes, and n is the number of trials. So if I have 10 trials in a binomial, the random variable goes from 0 to 10. 0, 1, 2, 3, all the way up to 10. Why? Because you can have 0 successes up to 10 successes, because there's 10 trials. Make sense? Yeah. Say yes. Of course it makes sense, Professor Barish, as I'm saying it. So if there's 100 trials, then you have from 0 to 100. So there's always one more. If you want to count the number of possible outcomes, it's always one more than the number of trials, because you have 0. It's always 0. 0 is always there. 0 means you have none of the outcomes is a success. Right? Even if it's very improbable for that to happen. Now, how do you calculate the probability for each of those possible outcomes? You can count them and divide by what? The sample space, right? The number in the sample space. You can do that, or there's a special formula for it. And here it is in the blue, dark blue here. And of course, they make it really hard to see. They also use a special notation here, which for some students could be confusing. Some books don't use this because some people are, some students are fixated on symbols, right? See the symbol pi here? They're going to think 3.14, right? Automatically, you see pi 3.14. And no matter how much a teacher says, in this case, it represents the probability of success in any trial, they'll still think it means 3.14. That's why in most statistics books, they've given up. They use small p for the probability of success, and the probability of failure is 1 minus small p. All right? But this book, they figure the people who are using this book are sophisticated mathematical savants. Everybody is good in math, and they are not tied to the idea that pi means 3.14. It means the probability of success. All right? So it's just a symbol in this case. It doesn't mean 3.14. Now look at the formula. The first formula, can somebody tell me what this formula is right on the left here? The first thing says n factorial divided by x factorial times n minus x factorial. What is that? We learned that in the last chapter. What is that?
Is that combinations?
Combinations. And what is the first number? If you're going to write it with, the combinations with that parentheses, with the top number and the bottom number, what's the top number? What letter would you use?
I don't remember. C?
N. In this case, it's N. N is it's a number of trials. In other words, if you had, let's say, 8 people, and you want to know, you wanted to group them into groups of 3, right? You did 8 given 3, right? Well, what's the group in this case? It's N, the number of trials. And then X represents the number of successes. So that would be you're grouping the 8 into 3 would be the same thing. It would be NX, all right? So that's why the formula ends up being like this, because it's n factorial divided by x factorial times n minus x factorial. Now, the rest of it is simply the probability of success to what power? The number of successes. Doesn't that make sense? It's the probability of success to the number of successes power. And then obviously, 1 minus pi must be the probability of failure to what power? The number of failures, which is n minus x. It's the number of trials minus the number of successes has to be the number of failures. Now, in the old days, before they had calculators, we used this formula. We calculated this by longhand. I remember doing this in school. Now, they had slide rules, but I don't remember how you use factorials with slide rule. I don't think you could. Maybe you could, I don't remember. But the important thing is mostly by hand this was done. That's why this formula still exists. But this is a formula that calculates what? The probability of a particular number of successes in n trials. Just one of the probabilities. So if I wanted to know, for example, what's the probability of getting no successes in n trials, it would be P0. And I just replace, now let's say it's in, let's make n 5. So let's say I'm repeating an experiment 5 times, right? And I want to know what's the probability of getting 0 successes when the probability of success is equal to 0.3. And it would be P0. The numerator would be 5 factorial. The denominator would be 0 factorial, but which, by the way, is 1. And then n minus 0, which would be 5 minus 0, that would also be 5 factorial. This whole thing would turn into 1, right? It all cancels to 1. And then we're left with what? 0.3 to the 0 power times 0.7, which is the probability of failure, to what power? To 5. So it's actually 0.7 to the 5th power will be the answer for this. But this formula gives you, for each of those values of x, which were, if n is 5, it would run from 0 to 5 for x, right? So you have your 0 case, you plug in 0 and you get your probability. You plug in 1 for x, you get your probability. You do so all the way up to 5 if n is 5. And then you have your probability distribution. You have a list of x's and you have the list of y's. Now let's go back to that. I just want to show you. Get back to the Excel spreadsheet. This, as I mentioned earlier, is a probability. This is a binomial distribution. Now, can somebody tell me how many trials are in this binomial distribution? That is Mo. Mo, are you there?
Here, I'm here.
All right, I'm going to get you to participate. How many trials are there in this binomial distribution?
Sorry, one sec. My computer's been on the fritz. Can you say it one more time?
How many trials are there in this binomial distribution, in the spreadsheet here? I'm telling you, this probability distribution is a binomial distribution. And what is the number of trials?
So then 2 trials because it's binomial?
No, that's just no. Binomial always means 2 possible outcomes per trial. How many trials are there in this case?
Okay, sorry, 10 then?
10, yes.
Okay, sorry.
It goes up to 10. It always starts at 0 and increases by 1, all the way up to the number of trials, which is 10.
That's not 11.
Nope, 10. No, it's 10. It always, remember the number of values, for a binomial random variable is always 1 more than the number of trials, because you always have 0 as a possibility. So no, if you see 10 here, that's 10 trials, period. Right? So don't be fooled by that. Now, what's underneath here, so that's your x. X for a binomial is always from 0 up to the number of trials. And the probabilities, each one of these is based off of what? The probability of success has to be known, right? These numbers will be different if the probability of success changes. Now, what is the probability of success in this case here? Now, it tells you here. Now, one thing I could have done, and I should do it here, I'm going to put above here, I'm going to use the letter P here, small p. Notice I use big P to represent the individual probabilities of the experiment, the binomial experiment, but small p is going to represent what? The probability of success. I'm not going to use pi, all right? That's because my key, I'm sure I could figure out where pi is on here, but I'm not going to bother with that. I'm just going to use small p. And I believe in this case it's 0.45. All right? So what do you need to calculate the binomial? You need 2 things. You need the number of trials, and you need the probability of success, and that's it. N and P. And that will determine any binomial probability distribution, period. Because that's all that's needed in the formula, N and P. Okay? Now, you'll say, well, how about 1 minus P? Well, duh, it's 1 minus 0.45 in this case here. So if you look here, there's a special function in Excel for a binomial. And it's called binomial.dist for distribution. You can actually just type in BINOM and then it'll show up. It'll show up as one of your choices. Now, what do they have inside of here? Now, what I'm going to do is I'm actually going to refer to this 0.45 instead of just typing it in, which I did originally. Let me just center this. All right. Now, N, of course, is what? This last number here, right? The last number here. So I could refer to this also. So let's look at the formula for this one here. The first position in this binomial distribution function is going to be what? The actual value. What's the value? Which is C3. Okay. Now I just typed in 10 because that was the what? That was the number of trials, right? But I could refer to 10 here, right? I could actually type in C, or excuse me, M3. M3, M3. Now, do I have to use one of those dollar signs? And if I copy the formula over, and the answer is yes, right? And I have to, because all of these, because the M is all of these numbers here are all in the same row, I'd have to put the dollar sign next to the M, right? Put the dollar sign right here. And 0.45 is represented by B, right? B2 here. B2. And again, I want the B to be fixed, right? And when I copy the formula over, I don't want it to move forward horizontally. So I'll put a B, a dollar sign before the B2. The last thing here, it's asking the following. It's saying, what's the term that they use? Actually, I'm just going to hit enter here. Oops, there's a problem. Let me see what the problem is. M3. So C3 would be what? It's this number here. It's referring to C3. Oh, I see the problem. It should be B2, right? B2. Let me make sure. Hold on a minute. B2. Oh, B2 was right. And then this number here should be M3, right? M3 is 10.
Is it because you put P equals point before the number?
Yeah, very good. Thanks for seeing that. So I'm going to put the, right. Well, this is just text, right? It's just text. So I'm just going to put P here. I'm going to say P is equal to. Actually, I'll just make sure it's right justified. Excuse me, wait a minute. Here. Right justify it. There we go. And this one here, I'm going to make it left justified. I'll put 0.45. Yeah. So good catch there. I'll make this left justified. There we go. Looks better now, right? So we're going to put in probability here. So now it's C2 is going to be where the probability is, right? So C2. And it should work now, right? It should be good. There we go. And then I'm going to copy this formula all the way down. Okay. Didn't change any of the numbers, stays the same. But now I have my probability of success here. I'm pointing to 10 as the number of trials, right? And I have my probability distribution. Okay. Now, one thing I didn't discuss with you is that each of these probabilities has a special name for it. It's called a probability. Well, in the language of discrete probability distributions, it's called a probability mass function. Each one of these, giving you individual probabilities. That's basically what it is. It's the probability. When I say P of 0, I'm saying what's the probability that X is equal to 0. Okay. If I point to this one, what's the probability X is equal to 3? What if I wanted to know the following question? What's the probability that X is no more than 5? No more than 5. Well, no more than 5 means less than or equal to 5, correct? I would have to add these 6 probabilities up from 0, 1, 2, 3, 4, 5, right? Or I could do what's called a cumulative mass function, or sometimes they call it cumulative density function. Regardless, cumulative. Cumulative in the discrete world means the probability that x is less than or equal to some number. So what if I wanted to know what's the probability? I'm going to put it right over down here. What's the probability that x is less than or equal to 4? I'll just put it, no, 5. Let's make it 5. And I'm going to put my answer right in here. All right. Now I could simply do a sum, right? I can do equal to sum. And I can simply run my, just do this, right? Sum from C4 up to H4. Hit enter. It just adds them up. Or I can use the cumulative distribution. And the way to do that is I'm going to do equal to, all right? And I'm doing in this cell right here, I'm going to do binom. Of course, I have to actually spell it right. Binom. Here it is. It's the very first one listed. Now notice it gives you in Excel exactly what is in each position. The first one, it says number S, right? What's the number S? Number of successes. S means successes in Excel. The number of successes. Now, I'm going to put what did we use? Do 5, right? I'm going to put 5 here. Number of trials is 10, right? Probability of success is 0.45. Now I could have, of course, pointed to things here, but let's just type in the numbers. And then it gives me this next option, says cumulative. If you type in the word yes in capital letters, it will give me a cumulative answer, which means from 5 all the way down, it'll add up from 0 all the way up to 5. So I'm going to type in the word yes. Close parentheses. Whoops. Hold on a minute. No, I'm sorry. It's not yes, it's true. I'm going to type in the word true. There's your answer. Now, in Excel, it doesn't really matter. It doesn't really matter too much here because you could so easily do a sum, right? But what if I wanted to know the following question? So cumulative, if you didn't have Excel, what if you just had this here and didn't have Excel available to you, and you needed just to simply add up these probabilities? Well, it's not a big deal, but isn't it easier to just do the cumulative function, right? Cumulative function. So if you have a TI-8384 calculator, you will notice it has a list of probability distributions, and one of them will say binom PDF, which is probability distribution function. The other one says binom CDF. The CDF gives you the probability if X is less than or equal to some number, which is the number of trials. So you can use either one of these. You can actually just do a sum, or you can simply use the, say, true here. Now notice for each one of these individual probabilities, I put false in. You see false? That means I want a PDF. I want an individual probability. If I put true in here, then it'll give me the cumulative probability. And I'll just do one more, and then we can stop, I guess. It's getting late. What if I did the probability that X is between 8 and 3, let's say. So 3. Well, actually, let's do it this way. This is even better. What if it looks like this? probability that X is between 3 and 8 include where the endpoint includes 8 but does not include the 3. Well, this is going to be equal to, tell me which ones I'm going to add together. We were simply using a sum here. So if I wrote it like this, X is greater than 3 and X is less than or equal to 8. Which ones am I adding together? Which probabilities?
4, 5, 6, 7, and 8.
4, 5, 6, 7, and 8, right? So it'd be these probabilities here, right? And then close parentheses and hit enter. But if you wanted to use the now if I wanted to do the cumulative, this, how would I do it? Now it's a little more complicated with Excel, right? To do it this way. Well, I would say this is equal to the cumulative probability of X is less than or equal to 8 minus the cumulative probability that X is what? Less than or equal to 3, right? 3. So it's a little more complicated to use with cumulative probabilities here, but it would work. All right. So you would do something like binom. And then you would put in 10. Number of successes, X star. The first one would be 8, right? It would be 8, 10, 0.45, right? And then we would say true, minus, and then we would say minus, do the same thing, right? Binom. And we would do 3, right? 3, 10, 10.45, true. Works. So you have to understand this cumulative density idea, that it's the probability of X is less than or equal to some value, all right? And so you could either, in Excel, you can either do it as a sum, or you can do it as, now what is the sum of? The individual probabilities, or you can do the difference of cumulative probabilities, which will give you the same sum. Okay, that makes sense? All right. So we'll continue with the spreadsheet next time. We'll do some more problems with binomial, and then I'll introduce you to probability distributions next time. And they are, let me just tell you what they are. One of them is called the hypergeometric distribution, right? And the hypergeometric distribution deals with the idea of 2 possible outcomes once again, but in this case, the probability of success changes from outcome to outcome. Now, I want to introduce this to you because I want you to think about the idea of a survey. This is a question I'll be asking next time. A survey with maybe, instead of the number of trials to be 10, we're talking about a survey of 1,000 people, like a political poll, all right? And I want you to think about next time, what's the difference between the binomial and the hypergeometric? All right, now, you can't answer the question yet, because I haven't talked about hypergeometric, but I can tell you the hypergeometric, the probability will change from trial to trial. All right, it will. So it's the alternative to the binomial when the probability changes. Still 2 possible outcomes, still limited number of trials, but the probability of success changes. So we're going to talk about that. And then the second one is called the Poisson distribution. It's a French word, P-O-I-S-S-O-N. Hopefully I pronounced it correctly, Poisson. And this is a probability deals with counting. The random variable is counting the number of something occurring, like the number of defects or something like that, where the probability is very small. Okay, so this is very useful also in real life. And Stephen, I know that you are a PhD. You might see a case where this probability distribution may be used. All right, Poisson is used sometimes in medical or biological research. All right, that's why I wanted to, again, because of your backgrounds, I think all of you can understand this pretty easily. All right, and then that's it. For next time, I'm going to continue with the binomial, introduce those other two to you, show you example problems, and that will take care of chapter 6. Okay, chapter 6 will be completed, and then we'll get into the most important part for our course. Will be the next chapter on the normal distribution. We'll talk more about that next time. All right, so I'll stop sharing. Did anybody have any questions or anything?
I have a stupid question.
No, nothing stupid in my class.
How did you get that 0.45?
It's given in the problem.
Oh, I see. See, that's a stupid question.
No, it's not stupid. It's a good question.
Okay.
You're thinking, did I miss something, right? Now, sometimes, I would say in almost every case, it's given, unless it's something that you know about, like the rolling of a die, right? You know what the probability of success of getting a 2 or a 3 or something like that, right? You know that. But in some cases, it has to be given because we don't know, right? So we come up with a long-term estimate of some process. So in this case, we're saying 0.45 for some process, for some binomial process that we didn't really discuss, right? What it is. But good question. That wasn't a stupid, it was a good question. Steve or Mo, do you have any questions before we leave?
Nope.
No? Okay. Okay, good. So again, I have posted some homework. It's very easy for chapter 5. Go ahead and start it if you have time, but it is due on Sunday, 11:59. So it's 25th. So make sure that you do complete it. It counted as 10 points. I will make sure that all the little projects we've done so far, I'll make sure all the grades are up to date by the end of, by Sunday or Monday, something like that. I'll make sure it's all up there so you know exactly what your grade is. Also, I think somebody, I think it was Rose, who asked me the question about the grade for the test. And what you'll see, and it was a good question she asked because she looked at the test grade, and then she looked at the overall average, and it seemed like the overall average went down. And the reason for that is that Canvas does not calculate points for overall average. It calculates percentages. So what I had to do, and I have to do this for all of your tests, not just for not the quizzes, but the tests, because I give you 110 points, which 10 of it's extra points, is I have to multiply your grade by 1.1 so that the percentage comes out correctly. All right? And that's why I do it. So your original grade will now look a little higher, but it's not, your original grade is your original grade. If you got a 90, it'll show 99 now, but it's still a 90. And it'll show up as a 90% now. I do that so that the percentage comes out correctly, all right? Because I don't want to, you know, when I give you 110 points, I want to make sure you get those extra credit points, okay? So that's how I do it. And math comes out correctly. And but I wanted to explain it to you so you'll understand what you see in Canvas. I'm not doing that with quizzes. The quizzes are all just regular percentage calculations. No problems with that. The projects are going to be like that. The final exam, if it has extra credit, again, I'll have to multiply it by some number and get it to look correctly. All right? All right. Anyway, I will stop the recording. There's no other questions.